terminology. It's not much, but some at least. So the first terminology, or the first thing that we want to define, is the net flow of a cut. So if you have a cut in the graph, then the net flow of the cut is the amount of flow out of the cut, out of the set S, minus the amount of flow into the set S. So for example, if you look at this set S, all the red edges flowing out, and all the blue edges are flowing in. And if you add the values on the red minus the values on the blue, you get 16, which turns out to be the also equal to the value of the cut in this case. The value of the flow, I'm sorry. Okay. So in this case, we saw that the net flow was equal to the value of the flow. Is this always the case, or is it coincidence? It turns out it's always the case. Whenever you have and this is our first step in trying to reconcile the flow and the cut, because we saw there's kind of a duality between the two. With the flow, you want kind of to maximize something. With the cut, you want to minimize it. And they seem to be kind of related. And so this is the first step where we are going to establishing this relationship. So the net flow for any cut, you have any cut and any flow, the net flow out of this cut is equal to the value of the flow. And this is essentially because of the conservation of flow. The way to prove it is by induction. So if your induction on the size of S, if your size of S is exactly 1, then the net flow is what is going outside of this S, and of course minus what's coming inside. That's the net flow, is what's going outside of S minus what's coming inside of S. But that's exactly the definition of the value of the flow. So that's not a big deal. Now suppose that you already have a set S, and there's a next step in which you are going to add another node to your set S. When you add this new node V into your set S, what's going to happen? Well, certainly all the edges that are going forward from S into V, they will be, before you have added the node V, will be forward edges, and they contribute to the net flow. And all the edges once you added V to this, to the node, you have to subtract these values from the net flow, because they are not anymore edges flowing outside of S. On the other hand, all the edges that are flowing outside of V, they didn't contribute before to the net flow. Now they have to contribute to the net flow. So now, of course, there are also cases where there are edges going from V back into S, and there are cases where there are other nodes flowing into V. You can handle it exactly the right way, the same way as we are doing here. Because the new net flow is the old net flow minus these red edges, because they don't count anymore as outward edges, plus these blue edges, because now they are the edges that are going outward. But the point is that we know for every internal node in the graph, what is coming in is equal to what is going out. So really, the value of the new net flow is equal to the value of the old net flow. So as you increase your set S, for any, for any size cut, the net flow is really equal to the size of the to the value of the flow. So that's not a bad thing. Now the other thing is called weak duality. It says that if you have any flow and any cut, then the value of the flow is never bigger than the capacity of this cut. The capacity of the cut is the sum of the edges that are going out of the set S. That's the capacity. The sum of the capacities on the edges that are going outside of S. That's the capacity. So why is that? Well, we know that the size of the value of the flow is equal to the net flow out of this cut. And the net flow is the sum of the flows that go out of S minus the sum of the flows that come into this set S. Now, whatever goes out of S, because we know the value of the flow is no more than the capacity, is less or equal to the sum of the capacities on the edges that are going outward. And the sum of the flows on edges that are coming into S, because we know the flow values cannot be negative, they're at least 0, is not going to be smaller than 0. So if you replace this red part with the sum of the capacities, replace the blue one by 0, we get exactly the capacity of the flow. So We know, therefore, that the value of a flow is never bigger than the capacity of a cut. So this is a very important thing to note, because we didn't really care how the cut was made. You take any cut and you take any flow, then the value of this flow cannot be bigger than the capacity of this cut. In particular, if you can find the flow and you can find a cut where the value of the flow is equal to the capacity of this cut, then this has to be a maximal flow. You cannot make this flow bigger, because if you made this flow bigger, you would have found a flow whose value is bigger than the capacity of this cut that you took. So the way to show that a flow is maximal is by finding a cut such that the value of the flow is equal to the capacity of that cut. All right. Now we go back to this thing called the residual graph. So the residual graph is the graph on which we try to find these paths. So what is the residual graph with respect to some flow? The vertices are the same as the original graph. Some edges remain, they go forward, and some edges go in the reverse direction. They become backward edges. So if an edge has a flow value that is smaller than the capacity, then we keep the edge in its direction, and we give it the capacity equal to the difference between the capacity minus the flow value. And if you have a flow value that is strictly positive, then we are going to create the backward edge for that edge, so the edge in the reverse direction. So if you look at this edge between u and v with a flow value of 7 and a capacity value of 9, in the residual graph, this edge becomes two edges, one that goes forward with capacity 2, one goes backward with capacity 7, meaning that on the forward path we can increase the value of this flow by at most 2, on the backward path we can decrease the value of this flow by at most 7. So here is an example how to get the full residual graph from a graph. So you see this edge 9, 10 becomes two edges, one that goes in the backward direction with value 9, one that goes in the forward direction with value 1. Oops, sorry. This edge over here, the 2, 2, becomes a backward edge with value 2. This becomes an edge with value 4, so together they form an edge with value 6, etc., etc. Okay, so the graph you see on the right-hand side is exactly the residual graph of the graph on the left-hand side with respect to the flow values. And this is exactly the graph in which we try to find augmenting paths, etc. Any questions about this? It's just a formalization of the algorithm kind of that I gave you. All right. So an augmenting path is a path in the residual graph from S to T. So here is one. So for example, from S you go down here, then you go up here, you go here, you go here, you go here, you go here. This is an augmenting path. It's called an augmenting path because you can augment the value of the flow by the minimal capacity on this path. That's why it's called an augmenting path. Okay. So the theorem that is at the core of this Ford-Fulkerson algorithm is the max flow mean cut theorem. It's a very important theorem. I'm sure that during your studies here, no matter whether you study computer science or communication systems, you will see the max flow mean cut theorem at least once more somewhere in some of your courses. It's just very fundamental. So it says the following thing. It says that the following items are equivalent. So suppose you have this graph and you have an assignment of capacities and you have two nodes S and T and you have a flow F. Then the flow being maximal is equivalent to the residual graph not containing an augmenting path. So if you find that the residual graph doesn't have an augmenting path, then that flow is maximal. And if the flow is maximal, then the corresponding residual graph does not have an augmenting path. Moreover, there is a cut in which the value of the flow is exactly equal to the capacity of the cut. And also, what it says, if you find the flow for which and the cut for which the value of the flow is equal to the capacity, then the flow is maximal, and the residual graph with respect to this flow does not have an augmenting path. So these three statements are equivalent. So we're going to prove these equivalent statements, and I'm sure you have seen the circular proof in many of your other courses. So we will prove that A implies B, that B implies C, and then that C implies A. So how does A imply B? Suppose that the graph is that the maximum, that flow is maximum, that there is no residual. Oh, what happened here? Interesting. Okay, so another bug. All right. So so we showed that should be, this contrapositive should be up here, not in here. So what it says is that instead of showing that A implies B, I'm going to show that not B implies not A, contrapositive. So not B means that the residual graph with respect to F contains an augmenting path. But if the residual graph contains an augmenting path, I can increase the value of the flow by the algorithm that I gave you. So F cannot have been maximal. So A implies B. B implies C. In other words, if the residual graph does not have an augmenting path, then there is a cut such that the value of the flow is equal to the capacity of that cut. All right. So suppose that this residual graph with respect to F does not have an augmenting path. So that means that T is not reachable from S in the residual graph. So we take all the nodes that are reachable from S in, in the residual graph. So obviously this doesn't contain T. And we call the other nodes that are not reachable capital T. That's the set of all the other nodes. All right. Now, of course, this capital S and capital T form a cut because they are disjoint and their union is equal to the set of all the vertices. So they are definitely a cut. Now, every flow, every edge that is flowing out of this S must be at capacity. Why? Because if the flow was not at capacity, then we could follow the edge in the residual graph. You said, whenever on an edge the value of the flow is smaller than the capacity, we can keep that edge. So if it were not at capacity, we could follow this edge outside of the set S. So some node outside of the set S would be reachable from the little s node first. And this is, of course, a contradiction because we know this blue part is all the nodes that are reachable. Nothing outside of S can be reachable. So there is no edge that is, so all the forward edges out of S have to be at capacity. On the other hand, all the edges that are going into S, the value of the flow has to be 0. Because if the value were not 0, then we can turn around the edge in the other direction. This is how we create these residual graphs. And if we turn around the edge in the other direction, again, we can reach a node outside of capital S through a node inside of capital S, which is a contradiction. So what did we see? We saw that every node, every edge flowing out of S in the original graph must be at capacity. Every edge flowing into S in the original class must have flow equal to 0. On the other hand, we know that the net flow is equal to the value of F. The net flow is the sum of the flow values that go out minus the sum of the flow values that come in. But we know all the flow values that go out are at capacity. All the flow values that are coming in are at 0. So the net flow is exactly the capacity of the cut. So we showed C from B. And finally, to show A from C, we use this weak duality. Suppose that there is a cut such that the value of the flow is equal to the capacity of the cut. By the weak duality, we know that the value of the flow is always less than or equal to the capacity of any cut. So if the value of the flow is equal to the capacity of some cut, this value must be maximal. If it were not maximal, then what would happen is that we would find a flow value that is even bigger than this one, and the value of this flow would be bigger than the capacity of this cut, which contradicts the weak duality. Okay, so therefore this F must be a maximal flow. And this proves the max flow min cut theorem. So what does it show? It shows that if the algorithm terminates, it's going to be correct. The value, well, if it really terminates, the value is correct. And I told you, Omid will put something on the exercise sheet where it seems to suggest that that if it terminates, it doesn't, well, a case where it doesn't terminate, but it converges to something, which is the wrong answer. But it doesn't terminate. It says if it terminates, then it's the correct one. So, now, back to the algorithm. The question is, how do we find an augmenting path? Well, finding an augmenting path is either you run depth first search or you run breadth first search starting from the node S. That way you can find an augmenting path. Okay? It turns out, don't use depth first search. Use breadth first search. Depth first search will give you trouble, and I will show you examples of that. So, but breadth first search works well. The next question was, if it terminates, does it so with the correct answer? We just showed it. That's the max flow min cut theorem. Now the question is, does it terminate? And if so, after how many iterations? Okay. Now, one of the very important special cases is when the capacities are integers. Now, what happens is if the capacities are integers, then the maximum flow is also an integer. Meaning that, you know, if all the capacities are integers, then it is possible to have a maximum flow. Well, it's actually, let's put it that way. If the capacities are integers, then there is a maximum flow with integer values. Because there may be an, you know, well, how is this possible? Well, you start with your original flow with the zero flow, right? So the original flow, the first flow that you put into this algorithm, the zero flow, is integer valued because all the flow values are integers. And the capacities in the residual graph are integer valued. Why? Because the capacities are equal to the capacities in the original graph. So that's okay. So we have shown that in the start of the algorithm, the flow values are integers, and the capacities in the residual graph are also integers. And these are the conditions that we will maintain during the induction. So in the induction step, the value of the flow is augmented by some residual capacity. So meaning that on some augmenting path, I'm going to add to the value of the flow the bottleneck capacity on that path. But I know that the bottleneck capacity is integer from my induction hypothesis. So I'm going to add the value to the value of the flow, which was an integer before, to the flow, another integer. So the new flow has also integer values. And the new residual capacities are also going to be integers because they are either equal to the flow values or the capacity minus the flow values, which is again an integer. So this is very good news because at every step, suppose that I have integer values as capacities. At every step, it's an augmenting path. Guys, can you please close your laptops? You guys know that, right? There are 4 examples here. Thank you. So, the capacities are integers. And we know that the maximum flow value is also an integer. And at every step, therefore, I'm increasing the flow value by at least 1. So the number of steps, if the capacities are integers, is at most the size of the value of the maximum flow. Of course, I don't know what the value of the maximum flow is, but I can at least give this bound. So, the question was, does it terminate? The answer is yes, if the capacities are integers. If so, after how many iterations? Here's the bad news. It's a bad news example. So here's a graph. The S is on this side, T is on that side. It's, you have two edges going out of S with capacity 1000. One edge between the middle nodes with capacity 1. Two edges coming into T with capacity 1000. All right. So I'm going to run this Ford-Fulkerson algorithm. Remember, the Ford-Fulkerson algorithm doesn't tell us how to find the augmenting path. It says, just find it. And I'm going to just be the devil's advocate and find it in the worst possible way. All right, so I'm going to go along this path over here to T. So I'm going, and the bottleneck capacity is 1. So it's going to go up by 1, down by 1. So I'm going to increase the flow value by 1. Then I'm going to go down here, go on this path in the reverse direction. I can do that because the flow value is strictly positive. And then come down here. Bottleneck capacity is 1. And then I'm going to go again over here, down here, over here. Bottleneck capacity is 1, etc., etc. So you can see the 1000 I put down here can be any large number. And you can see, so what is the maximum flow in this graph? What's the value of the maximum flow? There's 2000, right? You can put 1000 over here, 1000 over here. And at every step I'm increasing, if I choose my augmenting path in this stupid way, I'm increasing my flow value by 1. So after 2000 iterations, I hit the optimum. And of course, it's 2000 because I chose 1000 here. If I had chosen 10 to the 9, then after 2 billion iterations, I would have hit the... So you see, the number of iterations can be a problem. And one reason is, and in fact, this path is not such a bad path. It's a path that is dictated kind of by the depth-first search algorithm. Because in a depth-first search, depending on how you arrange these nodes, so this guy would put, these guys would go on the stack, and then you would take this guy would put these two guys on the stack, so we may go down here and then back here. So this could be a path that is given by the depth-first search algorithm. Okay. Now, even more bad news is that sometimes the algorithm doesn't terminate. Example on the exercise sheet. And it converges to some value which is very far away from the real value of the maximum flow. So this can also happen if you don't have integer values on the graph. It's a very interesting example. All right, but the good news, it's not just bad news, there's also good news about this. The good news is that so in two cases, let's say we take the shortest path, the smallest number of edges, or the fattest path. So fattest path is choosing a path with the largest bottleneck value on it. In either of the two cases, we can do better. So in the shortest path, with the best breadth-first search, the number of iterations will be 1/2 times the number of edges times the number of vertices at most. And if you take the fattest path, the number of iterations will be at most the number of edges times the log of the number of edges, roughly. Which is not bad. And then, of course, at every round you have to do certain operations, and you have to do it for the number of vertices, for the number of vertices altogether. So you have to kind of multiply this by the number of, by the number of edges, because of all the stuff that you have to do. You have to do at every round the breadth-first search algorithm, which is the number of edges. So you have to multiply this with the number of edges as well. But this is just the number of iterations. And U is the maximum flow, is the maximum flow value in this case. All right. Application. Bipartite matching. Some of you guys may recognize yourselves here. Okay, so what's the question here? You have N students that are applying for M jobs. So these are some of you guys that I got off the website that I can add you. And you have some companies on the right-hand side. eBay, Swisscom, Google, IBM, etc. All right? And what you want to do is each of these students, each of you guys, get several offers. Maybe you have written to all these companies or some of these companies, and you get offers. So what does it mean? It means that the first person here has gotten offers from eBay, IBM, and Amazon. And the second one got offers from Google and Yahoo, for example, etc. All right, so you got, each of the students gets offers from multiple companies. And now the question is there a way to match all these students to the jobs? Now, in order to match the students to the jobs, well, you at least want that the number of jobs is bigger than the number of students. Because otherwise, if each job is given to just one student, there will be some student that doesn't have a job. So this is at the very least. So the question is, can we have this? And I can imagine that this is an important problem. Now, interestingly enough, we can solve this problem with the flow algorithm. How? The way to do it is we're going to add a fictitious node S on the left and a fictitious node T on the right. And we are going to connect S to all the students and T to all the jobs. And then we are going to direct this graph from left to right. So all the edges go from left to right. And then what we are going to do is we are going to put capacity 1 on all these edges. Okay, so now this means what? This is a graph with integer capacities, 1. So this means that the flow values, when we run the algorithm, the maximum flow we get will also have integer values. And since it is an integer value that is less than or equal to 1 and bigger than or equal to 0, it means that the flow values will be 0 or 1. Okay. Now we run the Ford-Fulkerson algorithm on this. So let's see what happens. All right. Now I'm going to take this top pass over here. That's great. And here are sort of the various steps. So I took the top pass. Whenever you see a red edge, it means that its flow value is 1. And if it's not a red edge, the flow value is 0, except when I'm really in the middle of looking at the edges themselves. So the red values, so these are all the, these edges have value 1. Then I find another path over here, and then I find another path over here, another path over here, another path over here, another path over here. And then, well, it doesn't look like I can just follow a path forward. Well, I could. I could go down here and then go upstairs. Okay. So I just want to show you another kind of path. So here I can go down to this person. I can go up here, but I can then go back on an edge. And then go down again, and then go up. I can go back on every red edge because the value of the flow is strictly positive on red edges. But I can go only forward on the non-red edges, on the gray edges. So this is a valid path. A valid path means this red edge becomes now a gray edge, this gray edge becomes a red edge, and this edge over here becomes a red edge. Okay? And then, I don't know what happened here, because this was supposed to be a gray edge. So the next path I found is this guy, and that gives me the matching. Right, the matching is now complete. Now this is not the only matching. There may be other matchings as well. But this is just one matching. Okay. Well, nice algorithm. Now it's also the reason why it's also a nice algorithm is what is the max? So what is the number of steps maximally that this algorithm would use? What do you think? If you go back to what I showed you, if you have integer flows, the number of iterations that the algorithm will do will be at most the value of the maximal flow. So what is an upper bound and the value of the maximal flow here? If you think about S, how much flow can go out of S at most? Well, 8, or the number of students. So the value is, the maximum possible value is the number of students, which means that the number of iterations of this algorithm is at most the number of students, which is not bad. Okay, so why does this algorithm work? What is the connection between this algorithm and matchings? The connection consists of two parts. First of all, every matching is a flow. Why? If you have a matching is what? So you have this bipartite graph, and you match a node from this side with a node from the other side, and in a way that each node on the left is matched with at most one node on the right, each node on the right is matched with at most one node on the left. So every matching like this is a flow, because I can put a flow of 1 on all the edges of this matching, and I can put a flow of 1 on all the edges from S to the matched students, and I can put a flow of 1 from all the matched jobs to T. That completely satisfies it's a flow. Why is it a flow? It's important to understand why it is a flow. The reason is, this is a matching. So if something goes out of, let's say you have a value of, you have an edge from S to some student node, then you cannot have two edges going out of that student node, because it's a matching. The student node is matched to exactly one node on the job part. So the flow value is conserved at every student node. The flow value is also conserved at every job node. You cannot have two edges coming into a job, because it's a matching. Every job is matched with exactly one student. So it's conserved there too. It's really a flow. So, you see, every matching is a flow, and the value of this flow is exactly equal to the number of matched students. Now, every flow that you find during this algorithm is also a matching. So it's really the same thing. The flow in this graph is exactly equal to a matching. Why is every flow equal to a matching? Because it's a flow, meaning that when you add an edge into a student node, there is at most one edge coming out of that student. In fact, exactly one edge has to leave that student node because of the conservation of the flow. So every student node for which there is an edge from S to that node will have exactly one edge going out. So every student node, at least, is matched to no more than one job. On the other hand, for every job, because of the conservation of flow, if this job is connected to T, there is exactly one edge coming into that job because of the conservation of flow. So if you take the matched students and the matched jobs, there is exactly one edge between each, at most one edge between each pair student job, and exactly one edge between some student and some job. So therefore, this is a matching. So what it means is that a flow is exactly equal to a matching, so the maximum flow is equal to the maximum matching. All right. I think this is all I wanted to say today. It's pretty fast. I'm amazed how fast it went, because this is typically, and I think the reason it went fast is because of the slides that I've prepared. So this kind of concludes the flow algorithm. Now, one of the things you may wonder is, where do I use these flow? I showed you the Soviet example, which is kind of outdated at this point. But there is another example that is much more up to date. It's a kind of a modern way of trying to disrupt the flow of information. So maybe some of you guys have seen the friendship graph of Facebook. Have you seen that? This kind of blue graph with, yeah. So that's actually a very nice example, because if you look at that, you have exactly the same situation as in the Cold War today. You see, there could be a goal of some governments to disrupt the flow of information to their own citizens, or to some, or maybe not even to their own citizens, but to some geographic region. So what you want to do is you want to disrupt the flow of information into that region, if you look at sort of this friendship graph, in the most effective way. On the other hand, the goal of some other people may be to increase, to give as much information to this particular region as possible. So again, you have two completely competing goals, which you can kind of solve if you want with the max flow min cut. So in a way what it says is that there is some kind of there's some kind of justice, in the sense that the more information you can send to those people, the more work the disruptor has to do in order to disrupt that communication flow. There is a complete disparity between them, or parity, not disparity, complete parity between them, which is at least not too bad to know. There are many, many other cases. There is, if you want to optimize multicast traffic, or any kind of network that you have, you will have to do some kind of a flow algorithm in that network in order to optimize the flow of data on that network. So as I said, during your studies, you will at least once more see, sometimes even more than once more, see applications of the max flow min cut theorem. It's a very fundamental theorem in, let's say, the theory of algorithms. Next week, on Monday, I will start with some other algorithms that you have also seen. Minimum, this one you haven't seen, but the other ones you have seen in your discrete structure course, which is minimum spanning trees. Right? You have done that, I think. So we will take a fresh look at the minimum spanning tree problem, at some applications of the minimum spanning tree problem, in the same style as today, and at some algorithms and how they work and how you should implement them, etc., etc. All right, thank you.